A panel of polymethyl methacrylate is bolted in the long direction only at 50 degrees centigrade but between two other components with zero coefficients of expansion. What is the stress on the polymer at 0 degrees centigrade? Will the polymer break? Suppose this is the panel of polymethyl methacrylate and it's bolted on both ends in the longitudinal direction, and the coefficient of expansion of the materials at both these ends is 0. The temperature is decreased from 50 degrees centigrade to 0 degrees centigrade. Delta T is 50 minus 0, which is 50 degrees centigrade. We want to know if the polymer will break. So, as the temperature decreases, there will be some shrinkage. So, we need to know the coefficient of expansion of PMMA. PMMA has a glass transition temperature of 378 Kelvin. This is provided in table 8.7. 378 minus 273 degrees centigrade, which is 105 degrees centigrade. So knowing that the glass transition temperature is 105 degrees centigrade, we can say that at 50 degrees centigrade, the polymer is in the glassy state. Okay, so we are starting with the polymer in its glassy state and reducing the temperature from 50 to 0 degrees centigrade. So as we decrease the temperature, there will be some shrinking. So if we know the volume of expansion coefficient, we can use that to find out how much it will shrink. Table 8.7 also gives us coefficient of expansion for the glassy state, and this is the volume coefficient of expansion for PMMA. Is given as 2.6 times 10 to the negative 4 per Kelvin. Since the stress is only in the longitudinal direction, so the stress is only in this direction, only in one axis, we can divide the volume coefficient by 3 to get the coefficient of expansion in one direction, or the linear coefficient of expansion. So the linear coefficient of expansion for PMMA will be 2.6 times 10 to the negative 4 per Kelvin over 3, which is 8.7 times 10 to the negative 5 per Kelvin. So this is our linear coefficient of expansion. Multiplying the linear coefficient of expansion by delta T will give us the strain, because linear coefficient of expansion is the ratio of the change in the length to the original length for every degree change in the temperature. So 8.7 times 10 to the negative 5 per Kelvin times 50 gives us 4.3 times 10 to the negative 3. So this is a strain because strain is the change in the volume per original volume. So now we have the strain. So we can say epsilon, the strain is 4.3 times 10 to the negative 3. When a polymer is in the glassy state, we can visualize the stress strain curve to be steep, and it is going to be brittle because it's in the glassy state. A rapid brittle fracture minimal to no strain or plastic deformation. So because the temperature is being decreased when it is already in the glassy state, it's not going to give any strain or any plastic deformation, and it's not going to give us a clear yield point. Okay, so these are some expectations. So we are looking at a curve that is like this. For reference, you could see the figure in 11.6 for polyvinyl chloride in the glassy region. So in this case, the Young's modulus E is going to be almost a constant because that will be the slope of this portion of the curve. So Young's modulus for PMMA in the literature is given as 2.9 times 10 to the 3 megapascals. Multiplying the Young's modulus by the strain, we can calculate the stress. So 2.9 times 10 to the 3 megapascals times our strain is 4.3 times 10 to the negative 3, which gives us 12.47 megapascals. So this is the stress that it's going to experience, the panel is going to experience at 0 degrees centigrade. Now if we look at the tensile strength of PMMA, the tensile strength of PMMA is given in table 11.1. So tensile strength is the maximum strength that it can bear before breakage, and that for PMMA is 65 megapascals. So stress is 12.47 megapascals, which is significantly less than the tensile strength 65 megapascals. The polymer panel will not break. This is also probably why we use PMMA is also widely used in freezers.